Hey everyone, welcome back to this third and final video on assessing classifiers. In the first video, we introduced what classification was, and essentially again, it's just trying to draw fences to separate classes based off of features. So those features are uh, variables that are collected like height or weight, or here in our scenario, just toy data, an x coordinate and a y coordinate. We're differentiating between classes. We have in this notebook a red class, a blue class, and a green class that we want to differentiate against. In the second video, we constructed 4 different k nearest neighbors classifiers. Those classifiers resulted in decision boundaries. And we saw that higher values of k, we started with k as 15, we moved down through k as 1, but larger values of k reduced the influence of individual data points because there were more voting data points for each region in space. Smaller values of k, all the way down through k equals 1, reduced the number of voters eligible to vote on the group that a region in space belongs to, and so each individual data point became more powerful. And what we saw is that increased the flexibility of a model. And just like in regression, when we increase the flexibility of a model, we increase our risk of overfitting to the training data. That's building a model that's going to perform really well on training data, but won't necessarily generalize very well to new unseen data. In this final video, what we're going to do is we're going to go through and look at each of the models we built and discuss their performance metrics. Now, in our notebook, we've already computed the performance metrics. We just didn't stop to analyze them. But remember what we did with regression. Basically, we had 2 separate types, sort of umbrella types of error metric for regression. We had the training error, which described how well the model performed on data when it knew the answers ahead of time. And it had the test error, which described how well or estimated how well we expect our model to perform on future data when it doesn't know the answers. Remember that in the background, the computer is, if it's fitting a model, the computer is using the training error rate and trying to minimize that training error in terms of regression. And what we are most interested in is we're most interested in the test error rate, because again, the training error rate is biased. The test error rate is a better reflection of how well we expect our model to perform in the future when it doesn't have access to the answers ahead of time. The same is true here. We're going to pay most attention to the test error rates. And that's how we're going to assess models against one another. But so let's come back down to where we had built our model. Our first model was a k nearest neighbors classifier with 15 voting neighbors. And let's think about how we can consider trying to build an error rate or an error metric. So for our data points, when we were thinking about regression, we thought about each individual data point as having something called a residual associated with it. We were computing how far off our prediction was from what the true response value was. And those differences were residuals, and then we tried to aggregate those the residuals into one overall metric for the entire model. But when we think about classification, the idea of residual doesn't make sense anymore. Here's a red observation that was classified correctly. The error associated with that observation is 0. We didn't make an error. But here's a red observation that was classified incorrectly. It was classified as green. Now, how far apart are red and green? It's meaningless to say. And so all we can say is that this data point, we made an error on. And so we're going to count up either the data points that were correctly classified or the data points that we made an error on. And we're going to use those counts in assessing our model. So the big idea here, and the big difference between classification and regression in terms of performance metrics, is with classification, our predictions are either right or wrong. There's no degree to which we were wrong. And so we need new error metrics. So if we scroll down, so again, just as a reminder, the background here is showing you the classification model. The space in the background is colored according to the class at which these points in space belong to. So any point in this red region, we would predict as belonging to the red class. Any point in the green region to the green class, and any point in blue to the blue class. The first picture we drew with each classifier has the training data plotted on top of the decision boundaries and the decision regions. The second picture we drew has the test data plotted on top of the decision boundaries and regions. Now remember that the difference between the training and test data is that the model was fit using the training data. So the model knew the answers to, in this case, knew the classes. The model didn't know the classes in all of these cases. And so we're trying to build a model that will perform well on data when it doesn't know the answers ahead of time. We're interested in the second picture for each model. All right, so you saw in the notes that we use something called a confusion matrix when assessing model performance for classifiers. So a confusion matrix, I think it's worth trying to at least construct the start of one here. A confusion matrix has rows and it has columns. The rows correspond to the true class. The columns correspond to the predicted class. And so if we say that row 1 corresponds to blue, row 2 corresponds to red, and row 3 corresponds to green, and column 1 corresponds to blue, column 2 to red, and column 3 to green, we can start building out this confusion matrix. So this topmost entry is going to correspond to blue observations that were correctly classified as blue. Now, we may not get exactly the confusion matrix that the computer prints out because we have some data points that look like they're right on the edge here. In particular, this blue one looks like it might be falling into a green region. So we're going to make our best guess just from the visual. The computer will do an accurate job though. So let's say we have 1, 2, 3 blue data points that were correctly classified as blue. So we put a 3 there. Now, how many blue data points were classified as red? Well, no blue data points fall into the red region, so there are none there. And we're making sort of a judgment call here just from the visual that we do have 1 blue data point that's misclassified as green. So of the 4 total blue data points, we classified 3 of them correctly. We classified none of them incorrectly as red, but 1 of them we mixed up and guessed that it would be green. We can do the same thing with the red class. So the true red observations that were classified as blue, well, there's 1, 2, 3, 4, 5, 6 of those. The red observations that were correctly classified as red, 1, 2, 3, 4 of them. And then the red observations that were misclassified as green, it looks like we have 1, 2, 3 of those. And then we can lastly deal with the green observations. So there were no green observations that fell into the blue area. There were 1, 2 green observations that seemed to fall into the red area. And then there were 1, 2, 3, 4, 5, 6 green observations that we classified correctly. This is a confusion matrix. Again, the confusion matrix has rows representing the true classes, and it has columns representing the predicted classes. So if you notice anything along the diagonal here is a correct prediction, Anything off the diagonal is an incorrect prediction. It's an error that we made. And so hopefully that gives you a good idea of what a confusion matrix is and how it's constructed. What I did here is I had the computer build the confusion matrix on the training data and on the test data for our model. And so we can compute performance metrics using these things. So we have two separate types of performance metric when we're thinking about classifiers. We have overall metrics that consider the whole model. So these overall metrics consider all of the classes as being important. So we have accuracy and we have error. Both of these are rates. So they're going to be a metric that's a value between 0 and 1, 0 being 0%, 1 being 100%. If we wanted to find accuracy for our model, and let's say we want to do it for the training data, well, the way we do that is we look at the predictions that we got correct. So we have here 11, 14, and 14. We're going to add all those up. And we're going to divide by the total number of predictions we made. Now, we can get this in a bunch of different ways, but the easiest way to get it is just by counting the number of observations that were in the training data. So I'm going to ask for the length on X train, because that's what we call our training data set. Once we have that, the error metric, well, if we didn't get things right, we got them wrong, well, error is just going to be 1 minus the accuracy. And it's important to discuss error because if you remember in regression, all of our performance metrics were in terms of error, how bad is a model? And typically in these predictive tasks, we're trying to minimize an error rate. This is the same thing as maximizing an accuracy rate, but just for consistency across regression and classification, we talk about error most often. So we have an accuracy rate and an error rate for the training data. We also have the same thing for the test data. It's computed the same way. So if we're dealing with the test data, now these are observations where the model didn't know the answers ahead of time. The accuracy rate here would be 4 plus 4 plus 5. 4 blue observations that we correctly guessed were blue. 4 green observations that we correctly guessed were green, and 4 red observations that we correctly guessed were red, and 5 green observations that we correctly guessed were green, divided by the length now of X test, because these are the test observations. And then whatever we end up with for accuracy, we can compute the error as being 1 minus that. In terms of code, so we want to have Python do as much of the heavy lifting for us as possible. What we can do, and what I did here, and I encourage you to do this, is I defined the confusion matrix for both the training and the test set. We'll talk about this more when we actually discuss classifiers, building and using them. But for now, a confusion matrix, I'm using here this confusion matrix method. It's different than what you saw in Notebook 9 on evaluating classifiers. I use this pd.crosstab functionality there. It turns out that it's difficult to gain access to the entries in an object that's created by pd.crosstab. Much easier when you use the confusion matrix object. And so that's why I'm using this here. Confusion matrix takes the correct answers as the first argument. So the true response values from the training data set in this case, because we're computing the confusion matrix for the training data. And the second argument is the predicted classes. So now I'm using my classifier. I'm using this .predict method to say, hey, take in my data points, make a prediction for each data point and tell me what it is. So this will be my predicted classes. And I'll get a matrix out of that. The confusion matrix, the same one that we built earlier. We do this for training data, and we do this for test data. If we store the confusion matrix somewhere, then we can ask for its entries. And that's what we'll do here. So training accuracy. Remember that what we did is we added along the diagonal. So CM train 0, 0. This is row 0, column 0 of that confusion matrix. Remember that Python starts counting at 0, so we called it earlier in this video row 1 and column 1. We're going to add to that the entry in row 1, column 1. So that's the entry in the middle of the confusion matrix. And then we're going to add to that the lower right entry, the entry that's in row 2, column 2. Remember that the entries along the diagonal represent the correct predictions, and that's why the row number and the column number here match. We're adding up along the diagonal, and we're dividing by the total number of predictions that were made. So for the training accuracy, we're dividing by the number of training observations we had. To get the training error, we'll take 1 minus the accuracy. So you'll notice that I just copied and pasted the accuracy formula here. We can do the same thing with the test data. We have a confusion matrix on the test observations. The formula is the same other than referencing CM test instead of CM train. Again, we're adding along the diagonal. So row 0, column 0, row 1, column 1, row 2, column 2, and dividing by the number of predictions that were made. And so if we look, I'm just going to run this code cell. Nothing's really going to change. We can look at the accuracy and error metrics we have. So on the training data, we had an accuracy of 78%, which means we had an error rate of about 22%. On the test data, when we didn't know the answers ahead of time, we didn't do as well. We had a test accuracy of 52%, but a test error rate of 48%. So remember, we expect the model to do better on the training data than on the test data. And you might be saying, hey, well, we're only right about 50% of the time. That's kind of not great. But if you look back at the way we constructed our data, we had that the blue class was going to be 30% of our observations. I'm going to grab that for you here. So class A, which ended up being the blue observations, was 30% of our data. Class B was the red observations, that's 40% of our data. And class C is the green observations, that's 30% of our data. If you look back into the 9th set of notes, in there you'll see a statement about benchmarking. Remember, a benchmark is sort of like an initial model that we hope to beat. In that set of notes, it says one way to benchmark is just to predict the dominant class for everything. Here, the dominant class is red. And so if we predicted just blanket, every observation is red, we'd be right 40% of the time. That means we'd be wrong 60% of the time. So our error metric of 48% is actually pretty good compared to the benchmark, which was 60. So we've increased by 12 percentage points, or improved by 12 percentage points. So accuracy and error, those metrics reflect the model as a whole. But it could be the case that we don't care about all classes equally. Maybe we care about one class in particular. And that's where these other metrics like recall and precision come in. And in the notes, we also mentioned specificity, but we won't use that very often for our class. Recall and precision are going to be the most important for us. So recall and precision are specific to individual classes. We can actually compute recall and precision for the blue class, separately for the red class, and then a third time for the green class. Here, we're just doing it for the blue class. But I do want to talk to you about how these things are computed. So if we care most about the blue class, there are two objectives we might have. We might want to be really good at guessing correctly that observations in the population are blue. So if an observation is really blue, we want to capture that with our model. That's described by recall. So if you really want to make sure that you capture as many of the true blue observations as possible, you want to optimize for recall. You want a high recall rate. There is another metric that could be, well, we care about the blue observations, but we want to make sure that when we classify an observation as blue, that it really is blue. So think about that again. When we classify an observation as blue, we really want to be sure that it's blue. Versus recall, where when an observation really is blue, we want to make sure that we classify it that way. So these are two kind of competing metrics. And let's look at how they're calculated, which will clarify, hopefully, what I just said. So if we're computing recall for the blue data, remember the way that the confusion matrix is set up is true classes are along the rows. So true classes are along the rows. And along the columns now will be our predicted classes. And the way we set up our confusion matrices, it turned out that row 1 and column 1 were the blue classes. So here's blue and blue. And for the test data, here's blue and here's blue again. So if we want recall for the blue class, then what we're saying is we want to know out of all of the true blue observations. So let's deal with training data first, and then we'll deal with test data second. So out of all the true blue observations, so the true blue observations are denoted by this first most row, the top row. There were 11 plus 1 plus 3 observations that were truly blue. How many did we get right? We got 11 of them right. So we have 11 out of 15 is our recall for the blue class on the training set. If we're looking at the test set, well, how many observations were blue? Well, 4 plus 0 plus 0. And how many of those did we get right? 4 of them. And so our recall on the test data was actually really good. It was 100%. And so there's how we calculate recall. Remember, recall deals with the true class values and the proportion of the time we were actually able to flag those observations as belonging to the appropriate class. So here we looked at out of all of the blue observations, the observations that were truly blue, what proportion of the time did we capture them? We can also think about precision. So in precision, it's no longer the case that we're interested in all of the true blue observations. What we're interested in now is the observations that we classified as being blue. So I'm going to write precision in both spots and then we'll do the calculation. Well, how many observations did we classify as blue? Remembering that columns represent the predicted classes, well, for the training data, we had 11 plus 2 plus 1 observations that were predicted to be blue. How many of those were correct? 11 of them. So our precision for the blue class in the training data was 11 out of 14. That's a little bit better than the recall was. And if we think about the precision for the test data, well, again, how many observations did we predict as belonging to the blue class? Well, 4 plus 6 plus 0. And how many of those were right? 4 of them. So we get 4 out of 10, or 40%. So the precision here on the test data is worse than the recall was. So our model's really good at flagging blue observations when they're really blue. It picks up all of those blue observations. But our model isn't so great at distinguishing the other observations away from being blue. So if we have an observation that we've classified as blue, we're only 40% certain that that observation really is blue. So our model's really sensitive to the blue observations, and it's collecting some observations from the other classes and picking up and guessing that they're blue when they shouldn't be. All right, so there's a sort of conversation on class-specific error metrics, in particular thinking about recall and precision. These are not the only class-specific error performance metrics, but they are the two that we'll make most use of in our class. Okay, I'm going to clear this out, and then what we're going to do is, now that we understand the error metrics and we have these new baseline error metrics that do better than the benchmark model would have, where we just blanket and guess everything is red, let's see how our other models compare. Now remember, when we compare models against one another, we compare them based off of the test metrics, not the training metrics. Because in general, flexible models are going to beat less flexible models on the training data, but we don't know how they're going to perform on the test data. And so we look at the test performance metrics to determine that. All right, so the next, just before we move forward, again, just to recap one more time, there are two big types of error metric here beyond just training and test data, or training and test error metrics. There's the metrics that measure the overall model performance, that's accuracy and error rate, versus the metrics that are class specific. So if we're interested in just one class in particular, like the blue class here, we can look at metrics like recall and precision. The decisions we make when we consider accuracy or error versus the decisions we make when we consider precision or recall won't always agree. So it's important for us to know what our objective is before we start comparing models against one another. So is our objective just to build a model that gets classifications as correct as possible with respect to all the groups, or is our objective to capture true observations belonging to one particular class as often as possible? Is it to be really precise with our predictions? Excuse me. With our predictions with respect to one class? And so we need to consider that as we move forward. Okay, so we dealt with the k nearest neighbors classifier with 15 nearest neighbors. Let's take a look at the classifier with 7 nearest neighbors. I'm just going to regenerate the model. We'll compute the confusion matrix and the error metric. We're not going to go through those error metrics again. At least we're not going to go through the construction of them, because now we know how they're computed. But instead, what we'll do is we'll compare the models. So if we care most about just building a classifier that performs well with respect to all the groups, we're going to look at the accuracy rate and the error rate on the test data again. So our test accuracy is 56% here, and our test error is 44%. That's an improvement over the previous model, where we had an accuracy of 52% and an error of 48%. So now our error rate's gone down with the increased flexibility. So if we care to build a model that makes good predictions with all the classes in mind, The k nearest neighbors model with 7 voting neighbors is better than the k nearest neighbors model with 15 voting neighbors. In terms of the blue class, if we're interested in recall, the ability of the model to flag true blue observations, well, now we see a decrease in performance on the test data. Where we did have before 100% recall, now we have only 40% recall. Sorry, when we did have 100% recall, now we have only 50% recall. We also see a drop in precision here. So where we did have a 40% precision, now we have only a 28.5 or 29% precision. So in terms of just the blue class and our model's ability to handle the blue class versus the other classes, this new model is worse than the original model. When we consider all 3 of the classes, though, the model is better. So again, it's important for us to understand what our objective is to help us decide which performance metric we should really be paying attention to. If we look at the error metrics with 3 nearest neighbors, we're going to find a similar ability to compare. Now, if you look at the training error metrics, these are all improving. So the accuracy is now up to 82%, and the error is only 18%. But again, remember, we care most about unseen data. So our accuracy has suffered severely here. We're dropping to a 36% accuracy and a 64% error rate. This is even worse than the benchmark model that would just predict red across the board. So this is not a model we want to move forward with if we care about overall classification, overall performance with respect to all 3 groups. With respect to the blue class, again, we see drops in performance. So recall is the same as it was before. I think we had 50% before. So we're recalling half of the true blue observations still. And our precision is dropped even further. So this model does worse than either of the previous 2. There's no question. We wouldn't use a k nearest neighbors model with 3 nearest neighbors. That one's overfitting to the training data. And so the last model we had, if a classifier with 3 nearest neighbors voting on class is overfitting, then a classifier with only 1 nearest neighbor voting on the class that a region belongs to is definitely going to overfit as well. You'll see something interesting here. The training accuracy for a 1 nearest neighbors model is 100%. That's always going to be the case. A k nearest neighbors model where you're only allowing 1 nearest neighbor to vote will always have 100% accuracy and 0% error. That's because I'm voting on my own class. And so I know what class I belong to, and so I'm not going to get it wrong. On the test data, we have 44% accuracy and 56% error. Again, this is pretty bad. It's not as bad as the k nearest neighbors model with 3 nearest neighbors. But once we saw that 3 nearest neighbors was overfitting, we knew that 1 nearest neighbor would too. With the test data, our ability to recall the blue class has gone up. We're now at 75% recall instead of at 50% recall. And we got a little bit of a boost in precision as well. But overall, what it seems like is the k nearest neighbors model with 7 nearest neighbors voting on the class of any observation seemed to have the best overall accuracy and error metric. We had, where are we with 7? Yeah, so we had 56% accuracy and 44% error with that model. But the k nearest neighbors model with 15 nearest neighbors seemed to have the best performance metrics when we only considered the blue class, where we had 100% recall, 40% precision. And I just want to verify, yeah, precision dropped when we went to 7 and 8. And so there it is, a discussion on assessing the performance of classification models. A lot of what we talked about in the last week's notes and last week's video on assessing regression models still applies. We have two big umbrella types of error metric. We have training error. That's errors made, or a measure of the errors made by the model when the model knows the answers ahead of time. We're not particularly interested in the training error metrics, but some of our predictive algorithms, our model construction algorithms, will be driven by that training error. So the training error is really important to the computer. What we care about in selecting a best possible model is looking at the test error and trying to identify a model that minimizes the test error. So I hope this is helpful to you. Please let me know what you have for questions, and thanks for sticking with me through all three of these videos on classification. Thanks, everyone.